Now we are going to discuss about the forward biasing and reverse biasing of a PN junction. We know that in the PN junction formation, an electric field is created at the junction of the P side and N side crystal, which is directed from N side to P side. Due to creation of this electric field, majority charge carrier cannot cross the junction and current through the junction is equal to 0. But if the positive terminal of an external battery is connected to the P side and negative terminal to the N side of the PN junction, an electric field is created due to this external source of potential. And this external electric field is opposite to that of the contact electric field. As a result, if this potential difference is larger than that of the contact potential, this field is completely removed and hence majority charge carrier can cross the junction. That is, electrons from N side to P side and holes from P side to N side. And we get a current in the direction from P to N through the junction. The magnitude of this current is of the order of milliampere. The magnitude of this current is of the order of milliampere. If positive terminal of a battery is connected to P side and negative terminal to the N side, the junction is said to be forward biased. In this case, the direction of applied electric field is opposite to that of contact electric field. Thus, the value of barrier potential decreases across the junction, which allow the flow of majority carrier through the junction. This is called forward bias junction. The current through the junction is of the order of milliampere. Under ideal situation, the resistance of the junction under forward bias is equal to 0. Now reverse biasing. If the positive terminal of the battery is connected to N side and negative terminal to the P side, if positive terminal of the battery is connected to N side and negative terminal to the P side, then what happens? The direction of applied electric field and contact electric field are parallel to each other. As a result, the junction electric field or contact electric field gradually increases, due to which majority charge carrier cannot cross the junction. But this electric field does not resist the flow of minority charge carrier, that is, electrons from P side to N side and holes from N side to P side. Thus, a very low current is possible through the junction due to minority charge carrier. And it is of the order of microampere. The current through the junction due to minority charge carrier, current through the junction due to minority charge carriers is of the order of microampere. That means magnitude of current through the junction under reverse bias condition is very, very small, very, very less as compared to the current through the junction under forward bias condition. Because in forward bias, current is of the order of milliampere, but in reverse bias, the current is of the order of microampere. Therefore, we can say that a junction diode conducts current only when it is forward biased, and this property can be used to utilize in the rectification process. Thus, the junction diode conducts current only when it is forward biased, and this property can be utilized in the rectification process. Is it clear? So this is the forward bias and reverse bias. In forward bias, positive terminal of the battery is connected to the P side and negative terminal to the N side. As a result, contact electric field and that of applied electric field are opposite to each other. If this potential, applied potential, is more than that of contact potential, this field completely removed and hence majority surge carrier can cross the junction. And current through the junction is of the order of milliampere. But if the positive terminal of the battery is connected to N side and negative terminal to the P side, applied electric field and contact electric field are parallel to each other, which opposes the further flow of majority surge carrier through the junction. But this contact electric field does not resist the flow of minority surge carrier, and hence a very low current of the order of microampere flows through the junction under reverse bias condition. Since this current is very small as compared to that of forward bias current, thus we can say that a junction diode conduct current only when it is forward biased. This property can be utilized in the rectification process. Now we want to study the VI characteristics of a PN junction diode under forward biased and reverse biased condition. Now we want to study the VI characteristics of a PN junction diode under forward biased and reverse biased condition. So this is the circuit diagram to study the forward bias case. Okay, this is the PN junction, this is the P side, this is N side. This voltmeter read the potential that is applied across the junction. So this is the potential divider part, and this is the emitter which measure the current passing through the junction, and it is of the order of milliampere. You just see the polarity, positive side of the battery connected to P side and negative side of the battery connected to the N side. In order to study the reverse bias, we simply change the polarity of the diode. Now you see positive terminal of the battery is connected to N side and negative terminal is connected to the P side. This voltmeter read what is the voltage applied across the junction. And this emitter read the current passing through the junction, which is of the order of microampere range, because reverse bias current is very small as compared to that of forward bias current. You see, forward bias current is in milliampere and reverse bias current is of the order of microampere. Now if we draw the graph, this graph is like this. This graph is like this. If we want to draw the graph will be like this. So this is the forward bias current, milliampere, this is the forward voltage. This is the reverse bias current of the order of microampere, and this is the reverse bias voltage. This graph is already discussed in the current electricity. I think you can remember non-ohmic conductor, the conductor which does not obey the Ohm's law. During that study, we said that the junction diode does not conduct Ohm's law. That current no longer proportional to voltage through the PN junction diode. You just see, initially voltage increases, and when the applied voltage is less than 0.7 volt, current through the junction is practically zero. Once the applied voltage is more than 0.7 volt, current suddenly increases. Again in reverse bias condition, you just see, we increase the reverse bias voltage, but current through the reverse bias junction does not increase. It is of the order of microampere and very low current. Voltage increases, but current does not increase. Therefore, it is said that junction diode does not obey the Ohm's law. And this current is called reverse saturation current. This current is due to flow of minority surge carrier. But when the applied voltage becomes very large, of the order of 30 volt to 35 volt, then it is found that current through the junction increases very rapidly and the junction becomes very hot, and this condition is called Jenner condition. It was initially studied by a scientist called the Jenner, therefore this voltage is called Jenner voltage. So what are the important characteristics of forward bias curve? What is the important characteristics of forward bias curve? Some of the important features of forward bias curve is the VI characteristics. VI graph is not a straight line. That means junction diode does not obey Ohm's law. Initially, when the applied voltage is less than the cut-in voltage or threshold voltage, which is 0.7 for silicon and 0.3 volt for germanium. Can you remember what is this cut-in voltage or threshold voltage? This is the contact potential. This is the value of contact potential. Initially, when the applied voltage is less than the cut-in voltage or threshold voltage, the depletion layer play a dominant role in controlling the motion of majority surge carrier. And hence, a very low current flows to the junction. That means, when applied voltage is less than this contact voltage or cut-in voltage, this field does not remove completely. As a result, majority surge carrier cannot cross the junction easily. Therefore, very low current flows to the junction. Once the applied voltage is more than cut-in voltage, current increases almost exponentially, even for small increase in diode bias voltage. Here, the majority surge carrier feel negligible resistance at the junction and resistance across the junction becomes quite low. And resistance across the junction becomes quite low. So what are the important characteristics of PN junction forward bias curve? Number one, it is not a straight line, so it does not obey the Ohm's law. Current through the junction is practically zero when applied voltage is less than 0.7 volt for silicon and 0.3 volt for germanium. Actually, this 0.7 volt is nothing but the contact electric field potential, contact potential across the junction. Therefore, if the applied potential is not more than 0.7, this electric field does not remove completely. As a result, majority surge carrier cannot cross the junction easily and current through the junction becomes practically very low. Once the applied voltage becomes more than that of contact potential, that is 0.7 volt for silicon, majority surge carrier feel negligible resistance. Majority surge carrier feel negligible resistance while passing through the junction because that contact electric field is completely removed and current through the junction increases to a very large value. Next, the important features of reverse bias curve. You just see, we increase the reverse bias voltage, but reverse bias current does not increase. In this region, the current through the junction is due to flow of minority surge carriers, and we know that the number of minority surge carriers are very less very less in number, and hence, though we increase the voltage to the junction, the current through the junction due to minority surge carrier never increases. So it is said that when the diode is in reverse biased, the reverse bias voltage produces very small current of the order of microampere, which remains almost constant with bias voltage. That means when diode is reverse bias voltage produces very low current of the order of microampere, which remains almost constant with increasing the reverse bias voltage. This current is called reverse saturation current. That means though we increase the voltage, current never increases. That means current attain the maximum value, and therefore it is called reverse saturation current. It is due to the drift of minority surge carrier through the junction. Because we know that in reverse bias condition, the contact electric field increases in strength, due to which majority surge carrier cannot cross the junction. Number 2, when the reverse bias voltage across the PN junction reaches a sufficiently high value, what should be the high value? 30 to 35 volt. The reverse current suddenly increases to a large value. The voltage at which current suddenly increases is called breakdown voltage or Zener voltage. Why it is called breakdown voltage? Because when the applied potential, reverse bias potential is very large, this large potential difference across the junction create a high electric field, due to which it will pull the electrons, innermost electrons from the ends, the innermost electron from the p side of the crystal. এই সাইডটোত যিবিলাক innermost electrons আছে, সেই ইলেক্ট্ৰন বিলাক কি কৰিব, pull out কৰি দিব from the p side of the junction. As a result, a large number of electrons are created here and current through the junction becomes very large. But since this electric field pull out the innermost electrons from the p side of the crystal, once a normal junction diode attain this voltage, so this junction diode get damaged, because this electric field damage the internal lattice structure of the p side of the crystal. And it was initially studied by Zener, and therefore this voltage is also called the Zener voltage. So at this voltage, the kinetic energy of the minority surge carriers increases to high value, and then knock off electrons from the covalent bond of the semiconductor on the p side of the crystal. Thus, current through the junction diode increases suddenly, damaging the junction diode. That means at Zener voltage or at the breakdown voltage, since the electric field becomes very high at the contact of the two crystal, due to this high electric field, kinetic energy of the minority surge carriers, that is electrons, on the p side of the crystal increases to very high value, and then knock off electrons, and these highly accelerated electrons collide more frequently with the atoms on the p side of the crystal, and then knock off electrons from the covalent bond of the semiconductor. Thus, current through the junction diode increases suddenly to a large value. But once this voltage is achieved, that particular junction diode get damaged, because this high electric field damages the internal lattice structure on the p side of the crystal. Okay? So this is the reverse bias characteristics of PN junction